This case study of an antibiotic filter manufacturer that developed an acceptance sampling control plan to reduce costs and while maintaining quality at the customer is brought to you by JMC Data Experts. A manufacturer of antibiotic filters used to remove bacteria from blood determines the level of a contaminant in 100% of their filters using a long and expensive gas chromatography measurement. The contamination level is a key quality characteristic and must be below an upper specification of 4 parts per million. Like many medical device manufacturers, they ask themselves, would it be possible to measure a fraction of the parts in each lot instead of 100%, and still determine if there were defective parts in the lot? Acceptance sampling is a quality control tool that allows you to characterize a lot as either good or bad based on the information in the small sample taken from the lot. A typical acceptance sampling control plan measures several parts to estimate the mean and standard deviation of all the parts. Assuming normality, we use these values to estimate the normal distribution that describes the population. The distribution can be used to predict if a lot will or will not meet certain quality standards. In the example shown, we might reject the lot if the upper specification was 6 ppm, but find the lot acceptable if the upper specification was 8 ppm. However, in the case of our filter manufacturer, we see the distribution of their data is not normal. The problem contamination levels are flyers above the main body of the data. This leads to inaccurate conclusions. For example, the CPK of 3.02 implies a parts per million defect level when the observed defect level is actually 0.62%. But all is not lost. We can still develop a non-parametric acceptance sampling plan based on the data we have. If all 16 measurements in each lot are shown over time, we see that most lots are good, as shown in red, with every filter under the specification of 4 ppm. Next, we look for a natural cutoff point to act as a warning that the lot is bad, meaning that there is a high likelihood at least one filter in the lot is out of spec. These bad lots are shown in blue. The data pointed towards 2 parts per million as our cutoff or warning level in our control plan. But how many filters out of the 16 filters in each lot do we need to sample for our control plan to work? 4 possible sampling plans were considered. At the extremes, we looked at the current process of 100% inspection, and then 0 inspection to bracket the calculations. In the middle, sampling half of the 16 filters and 5 of the 16 filters was evaluated. The control plan was simple. Reject the lot and measure all 16 filters if one of the sample filters exceeded the 2 ppm warning level. How effective would each of these sampling plans be? We can compare the 4 plans by considering the key trade-off for any acceptance sampling plan. How many measurements are saved versus what is the expected defect level at the customer? We evaluated how each of the 4 plans would have worked on 202 historical lots of filters where all filters were measured. The defect levels ranged from 0 to 0.62%, as the number of tests saved changed from none to all 3,220 filters. Of secondary importance was the false alarm rate, which was the number of times a lot was rejected, but there were no out-of-spec filters in the lot. In the end, the plan to sample 5 filters from each lot was selected. The defect rate at the customer was estimated to be 0.35%, which was below their acceptable quality level of 0.5%, therefore meeting their quality requirements. The calculated number of tests saved was 2,054, resulting in a cost saving of over $130,000. If you would like to implement an acceptance sampling control plan to reduce costs in your high inspection process, or if you have any questions about this case study, contact us at JMC Data Experts.